Okay, as far as it goes, at this point for integration, we have the regular integration that you know, we have integration of trig functions, we have integration of exponentials, we have U substitution, we have the power rule, integration by parts. In this class, we've talked about trigonometric integrals, trigonometric substitution, partial fraction decomposition, and essentially at this point, we have all the algebraic tricks that we can possibly come up with. So now the question is, can we integrate everything that we want to integrate? And as it turns out, no, there are still functions we cannot integrate, but there are no more algebraic tricks we can learn, which means we need to come up with other ways to try to figure out the value of the integral. And a couple of things. First off, from your exam's perspective, on your exam, essentially, I'm just going to give you like 10 or 15 integrals and say, integrate all of these. You need to show your work, showing the correct method to solve it, and then solve it all out. Because that's ultimately the goal, at least for this chapter, to be able to integrate using all the rules that we know. But then the question becomes again, what do I do if I have something that I cannot integrate? And there's a couple ways to go. One thing for this week, the first section you have is on integral tables. I'm actually not going to make a video of that. Essentially, the idea is, if I wanted to integrate something like the square root of 1 minus x squared dx, looking at it, I could say, okay, U substitution and integration by parts are out, but that's a square root, that's a 1, which is a square, that's an x, which is a square. They're both squares that kind of looks like the Pythagorean theorem. So I could probably try to do some type of trigonometric substitution and solve this out. And you can algebraically do that. But because a lot of these become repetitious and look the same, people have kind of created tables of formulas that basically tell you, if integral looks like this, solution should look like this. All the integral tables are in your book. If this was a seated class, we might spend a few minutes just kind of running through the books. It's not seated, so we're not going to do that. But basically, you can use those integral tables if you want, but all those integral tables are based off of integrals that we can already solve with the tricks we know. Which means, even if you don't know the integral tables, you can still solve the integrals out and get the same answer. The table will just save you a little bit of time. It's a shortcut. So those, I just gave you some problems to do to see if you can integrate by hand if you want, or see if you can kind of mess around with the integral tables and find the solutions faster. That's kind of up to you which way you go. In this case, we want to start looking at functions that I don't know how to integrate and see if there's something I can do. As an example, suppose I wanted the integral from 0 to 1 of e to the negative x squared dx. And right away, if it was e to the x or e to the negative x, simple exponential integral, not a problem. E to the negative x squared, once that x is squared, that's a problem. U sub integration by parts won't work because there's nothing down in front for me to have as part of my substitution. Trig integrals, trig sub, not going to work there. Integration, partial fraction decomposition is out. So there's really no tricks I can use, and as it turns out, you can't, using an integration trick, solve that integral out. So what do? And one thing we can do is kind of go back to the beginning where we said, if I can't solve the integral, maybe I can approximate it. And if nothing else, I'll just go with my approximation as my best guess. And as an added caveat to that, because it isn't Calc 1, it's Calc 2, maybe once I approximate my integral, I can then approximate maybe how much error there is involved in my approximation. So at least I know how close to the solution I actually am, even if I can't find the solution. So we're going to look at tricks like that, which we'll use for this. But for the purposes of this, I'm going to use easier integrals that we can probably solve by hand, just so that the calculations, which are going to have to be done in the calculator and all that, aren't as challenging to write out because I'm doing this by way of video. But let's see. Suppose I have, well, they'll say the integral from 0 to 4 of, we'll just do something nice, x plus x squared dx. And again, we could certainly solve this out by hand using our tricks, but in this case, we're just going to approximate it. And when you were in Calc 1, generally they would say, graph it, that's a quadratic. Let's see, at 0, I get 0, at 1, I get 2, and the zeros are at 0 and -1, that's a cubic, I'm sorry, no, that's a quadratic. The zeros, if I factored this, that would be x and 1 plus x, so there's a 0 at 0 and a 0 at -1, which means if my 0 is there and there, okay, then I can be reasonably convinced it just looks like that. Good. And now I want to find the area under the curve as I go from 0 to 4. And if this was 271, Calc 1, we would just draw rectangles and be good to go. The problem, and I'm not going to draw on this with rectangles and make it messier. I'll draw my red darker so I can see the video. There we go. We recall from Calc 1, rectangles are good approximations, but they can be really off based on the steepness of the curve and things like that. And in Calc 1, you used a left-hand endpoint, a left endpoint, a right endpoint, and then a lot of times you would use the middle, the midpoint, as the value for your approximation to try to eliminate as much error as possible. Here, we're going to use a similar approach, and I'll just pick an arbitrary value like right in here. We'll say this is x sub I, and this is x sub I minus 1. If I drew a rectangle, left-hand endpoint would look like that, and I'm missing a whole lot of area. Right-hand endpoint would look like that, and I get a whole lot of extra area. Midpoint, maybe right about here, would get me that rectangle, where maybe I'm missing area, I've got some area here, so it's closer. Essentially, the problem is I'm using a rectangle that has a horizontal top to approximate something that's clearly not horizontal. So it would be better if I use something with a non-horizontal top. And in this case, we can use a line segment here between 2 points. Now, if I use a line segment, and in particular a slanted line segment between those 2 points, that gives me a better shape to approximate that area right there. And now, these 2 sides of this shape are clearly parallel. That's slanted, that's not, which means those are parallel, those sides aren't. It's a trapezoid. And now, instead of using rectangles to approximate my integral, I can use trapezoids. I'm going to assume you all remember the formula for the area of a trapezoid. If not, it is 1/2 height times base 1 plus base 2. Keeping in mind for this, the height will actually be right here. That's my height, which is also going to be my delta x as I add up these rectangles to these trapezoids to approximate it. This will be base 1 and this will be base 2. Those are the function values. So now what I'll do, and now we'll expand this picture a little bit. I have that curve as I go from 0 to 4, which we've established. At 0, I get 0. It's just going to curve up. At 4, I get 16 plus 4, which is 20. And it'll look like that. And since I went 0 to 4, I'm going to let n equal 4 and create 4 trapezoids. So I need to pick values. If I break this up into 4 intervals, That's 1, that's 2, that's 3, these aren't spaced out very well, and this is 4. And there are my 4 trapezoids. Now I sketch each one and find its area. I'll just do these 2, so again, this doesn't look too terrible. But now, I can just add up the areas of those 4 trapezoids to approximate this, to approximate that integral over there, and then we can generalize that to see if I can find a nice way to write these out if I want to use more trapezoids. Here, the area of the first trapezoid, which would be this one right here, would just be, let's see, f sub, we'll say 0 here of x, or actually we'll just say maybe this way, f of 0, which is the height here, plus f of 1, which is the height here. Those are my 2 bases. I have a 1/2 on the front, and I multiply that, the height, which is delta x, but for each of them it's 1. So that's just 1. Then I add on the second trapezoid. It's still a 1/2. Delta x is still 1. Now I'll get this trapezoid. The left base is f of 1. The right base is f of 2. Now I do the third trapezoid. 1/2 and 1 are the same. But for the third trapezoid, I use f of 2 and f of 3 as my bases. And then for the last one, I use f of 3 and f of 4. And now I throw all of that into my calculator and see what I get. But before we do that, looking at this, we can see, to maybe make my calculations easier, every term has a 1/2 in them. So I'm just going to factor the 1/2 out. Every term has a 1, so I'll factor that out, it just disappears. Now what am I left adding? F of 0 plus f of 1 plus f of 1, which means there's 2 f of 1s, but then there's 2 f of 2s. I'm going to run out of room. There's 2 f of 3s, and then there's only 1 f of 4. And again, I could certainly find all of these individually, add them all up, and get an approximation for my area. But if I manipulate this algebraically, this is somewhat easier to write out and calculate. It saves me time. If I then do that for this, I get a 1/2 on the outside. F of 0, that's 0 plus 0, which is 0, plus 2 times f of 1. 1 plus 1 is 2, plus 2 times f of 2. 2 squared is 4, 4 plus 2 is 6, plus 2 times f of 3. 3 squared is 9, plus 9 plus 2 is 11, plus 1 f of 4. F of 4, 4 squared is 16 plus 4, I get 20. Now, that is 1/2 of, 2 squared is 4, plus 6 times 2 is 12, 2 times 2 is 4. 6 times 2 is 12, 2 times 11 is 22, that's just 20. 20, 42, 54, 58. And half of 58 is 29. And there's the approximation for the area underneath that curve. If I wanted to make that approximation, what would I do next time? Well, maybe instead of using 4 trapezoids, maybe I'll use 8 and say we'll divide this into 2 separate ones, and we'll do that. And then maybe, if that approximation isn't good enough, take those 8 trapezoids and make them 16. And we kind of get the idea here, similar to what we did with rectangles. But again, it would be better if I could somehow generalize this to a formula. And if we look down here, there's always a 1/2 on the outside, which is obvious, it's coming from this. There's always an h on the outside. For us, it was 1. In general, that will just be delta x. The change, the length right here. And then on the inside, the leftmost endpoint of my interval, that function value will only be used once as the leftmost endpoint of the leftmost height of the leftmost trapezoid. The rightmost endpoint will be used once as the height of the rightmost trapezoid. All the other heights will be used twice as the left-hand endpoint of one trapezoid and the right-hand endpoint of another trapezoid. Which means I can actually generalize this to a formula. Where we can say, we'll generalize what's called the trapezoidal rule. And we will say the integral from a to b of f of x dx is equal to, well, let's see, I always have a 1/2, I always have a delta x, times f of, here we'll say x sub 0, plus 2 times f of x sub 1, plus 2 times f of x sub 2, all the way out to 2 times f of x sub n minus 1, and then f of x sub n. And I'm going to check to make sure I'm using the same notation as your book. I am. Good. Where again, we have this, you can write that as delta x if you want. If you prefer to think about it in terms of the trapezoid, you can write this as an h. If you want, we understand that delta x or h is the length of the interval divided by the number of trapezoids. You can write it that way. All forms are the exact same. It's entirely up to you how you're going to write it all out. Now, since I don't want to change it again, I'll just leave the h in there. And then again, leftmost endpoint and rightmost endpoint, their function values get used once. All of these values on the inside get used twice. And all things being equal, again, this is no different than using rectangles with the left endpoint, the right endpoint, or the midpoint. The formula is just slightly different because of the way the trapezoids are defined. But once you have that, this is all calculational. So I'm going to kind of leave the calculational aspect to you as students. Because again, this kind of leads us to a second question. And the second question is, how good is my approximation going to be? Because again, I would point out, while we did the trapezoidal rule for this, in actuality, I wouldn't use the trapezoidal rule for this. I could just solve that integral out. I want to use this for integrals that I can't solve out, like if I just replace this with e to the negative x squared. I could still find the function value, or even approximate the function value at different n values, at different x values, plug them in here and get an approximation for the integral, which is not the best solution, but it is an approximation. And then, well, the follow-up is, how good is that approximation? How close is it to what the value of that integral should be? And I'm going to leave off the actual calculational aspect of this because it's not important for this. But as it turns out, there is a formula to find the error of the trapezoidal rule. And probably going to need more room because there's a lot of words here. So we'll fill the whole board. I'm trying to use the same notation as your book so there is no confusion. If K is a positive real number such that the absolute value of the second derivative of x is less than or equal to k for all x's in AB, then an upper bound for the absolute error E sub t is approximated by I can't read my own writing. In approximating the integral from a to b of f of x dx using n trapezoids is the absolute value of E sub t is less than or equal to k b minus a cubed all over 12n squared. If k is a positive real number such that the absolute value of the second derivative of f for all x's is less than or equal to k for all the x's in the interval a to b, then an upper bound, not the least upper bound, but an upper bound for the absolute error E of t in approximating the integral with n trapezoids is right here. And we're going to go through this in a minute. I know this can look a little confusing, but the idea is I have an integral that I can't solve. I use the trapezoidal rule with 10 trapezoids to approximate the area. I want to know how close I am to the actual value. What I have to do is, k is a number which you have to find, which we'll explain in a minute. B minus a is the length of your interval, cubed. N is the number of trapezoids squared times 12. And whatever that number ends up being, that is the upper bound on the absolute error for the trapezoidal rule. So whatever value you get, add or subtract the error, and that will give you a range of values for the actual value of the integral. This is essentially computational in nature. The only trick is finding this k. And the way it works is, k is entirely based on your second derivative. So given a function, you find the second derivative, then you find the upper bound of that derivative on your interval. And I'll point out at the start, there are different algebraic tricks you can use to do that. We're going to go through one so it's clear on how this works. But there's lots of different tricks you can try. So, for the sake of argument, here we're not going to use the trapezoidal rule and make this really long. We're just going to try to find an upper bound on the error. Let f of x equal 1 over x on the interval 1 to 5 with n equals 10 trapezoids. So assuming I use the trapezoidal rule for this function on this interval with 10 trapezoids, I want to find an upper bound on my error. And I do again point out, I wouldn't use the trapezoidal rule on this, I would just solve it all out. Here we're just using this because the algebra will work nicely. But what I have to do is, first, well, I already know what a and b are. I already know what n is. I just need to find k. So to find k, I take my function, f of x equals 1 over x. I have to find the second derivative. So f prime of x is, that is x to the negative 1, bring down the negative 1, lower the power by 1, that's negative 1 over x squared. Then find the second derivative. That's negative x to the negative 2, bring down the negative 2, negatives cancel, you get 2 canceling the negative, lower the power by 1. This is your second derivative. Now you have to find the maximum value of this derivative on your interval a to b, which in this case is 1 to 5. And again, how you choose to do this varies based on the problem. In this case, 2 over x cubed is clearly a decreasing function. As x gets bigger from 1 to 5, 2 over x cubed gets smaller because the numerator 2 is constant. Put it another way, if you plug in x equal to 1, you get 2 over 1 cubed, which is 2. If you plug in x equal to 5, you get 2 over 5 cubed, which is 2 all over 125. And again, this is clearly, it's clearly going to be decreasing, which means to find the maximum value on the interval, I can use the left-hand function value as my maximum. Because I know every function value is always less than or equal to 2. So now I'm going to let k equal 2. Now I can find the bound on my error. My absolute error is less than or equal to k, which is 2, times b minus a, which is 5 minus 1 cubed, all over 12, times n, which is 10, squared. And then you just throw that into your calculator and hit enter. 5 minus 1 is 4, 4 cubed is 64, times 2 is 128, over 10 squared, which is 100, times 12, which is 1200. And then for the sake of argument, that is 64 over 600, which is 32 over 300, which is 16 over 150, which is 8 over 75, which can't be reduced anymore. Or if you're just going to use your calculator, 8 divided by 75, 0.106 repeating. So there's the bound of my error. So the way this works is, assuming I had used the trapezoidal rule on this interval with that many trapezoids, whatever solution I got, add or subtract my error, and that would be the interval in which the actual value of the interval exists. I don't want to take the time, because this is already long enough, to do a whole problem out, but it should be pretty straightforward. The only real trick to this is finding this k. And it's entirely based on your second derivative. And again, you just have to understand what the derivative looks like and figure out ways to maximize it. You could try taking the derivative, which would be the third derivative, because if you have to maximize a function, you use the derivative. So if you're trying to find the maximum value of this function, you could use the derivative and go from there. In this case, again, because it's a decreasing function, we could just use the left-hand endpoint. If it was an increasing function, you'd use the right-hand endpoint. So there's lots of algebraic tricks you can do, entirely based on what your function, and by extension, what your second derivative actually is. But then, the question maybe, and the way this algebraically works, pretty much always boils down to the same thing. Meaning, going back to pre-calc, you're given the equation of a line. They give you x, you tell them y. Or if they want it to be confusing, they give you y, you tell them x. Because you have two variables, given one, you find the other. This is really no different from a problem perspective. If, say we did the same thing, which hopefully I will remember, 0.1067. So we had ET, absolute error, was less than or equal to 0.10, we'll just round it to 0.107. Well, if I look at this, that's my absolute error, which I found. K is always a constant. I find it by way of the second derivative, so that's not going to change. B and A are my interval. Those are constants. They're not going to change. N is the number of trapezoids. That can change based on the number of trapezoids I have. Which means the way we generally use this is, 1, use the trapezoidal rule to approximate the value of the function, the integral, area under a curve, and then use this to approximate the error to get an idea of the actual value of the function, the integral. Or alternatively, if I know how close I want my approximation to be, well then I'd be given the error, and I can find n, the number of trapezoids I would need to use in order to get within the error that I want. So as an example, suppose I'm solving this out and I say, oh, I'm within 0.107. That's good. I'd prefer it if my absolute error was less than or equal to 0.01. How many trapezoids would I need? Well, then I just plug in here and I solve for n. So if we do this quickly, 0.01 is less than or equal to k, which for us we said was 2. 5 minus 1 cubed, all over 12n squared. And then I solve. Multiply the n squared over the 12n squared over here, and I get 12 times 0.01, which will be 0.12 n squared is less than or equal to 2 times 5 minus 1. I'm sorry, we'll just solve this all out. Make it easier. 5 minus 1 is 4 cubed, which is 64 times 2, which is 128. Divide by 0.12, n squared is less than or equal to 128 divided by 0.12, which I can then put into my calculator on 128 divided by 0.12, and I get 1,066. So n squared is less than or equal to 1,066.7. So then square root both sides, second square root second answer, and I get 32.6. Which means if I want to be beyond, I have to go beyond this to make sure I get within the error I want to make the error smaller. So I would say let n equal 33. And if I let n equal 33, then I will be within 0.01 of the actual value of the integral. And there's kind of this push-pull idea here where, on the one hand, you want to calculate out something that you can't calculate by hand, using this approximation trick, which can be cumbersome, so you understand you accrue error, but at the same time, you don't want to have too much error. So where do you draw the line between the number of trapezoids you have to use and the error that you get? Maybe getting this error is okay, so I'll go with 10 trapezoids. I want better error, so I'll use more trapezoids, and I kind of decide where I want to delineate there. I don't care that much. I'm doing less work, fewer trapezoids. I care a lot because all of you are engineering students and you're going to be like building bridges or something. I want to be really accurate. I'm going to use more trapezoids to make sure this approximation is better. And that's kind of how this works. I'm going to stop there again. This is mostly calculational in nature. Once you know the trapezoidal rule in the error estimate, it's really just a little bit of algebra and a whole lot of plugging and chugging with a calculator. There is another approximation trick called Simpson's rule, which I'm not going to put in this video because this is already too long. Either later today if I'm free or tomorrow, I will make a video going over Simpson's rule and Simpson's error estimation too, and then I'll upload that as well.